Okay, welcome everyone. Hello, thank you for joining us today. My name is Nicole Shuford. I'm from NASA Langley Research Center. I'm going to be your moderator today for this webinar on Biocybernetic Frontiers, NASA's Physiological Adaptive Systems for Performance Enhancement and Conflict Resolution. As part of my role here at NASA Tech Transfer, I work with NASA scientists who have developed new technologies that may have applications outside of the aerospace industry. Our presenters for today are Dr. John Muñoz, Dr. Alan Pope, and Chad Stevens. Dr. John Muñoz has an extensive background in human-computer interaction, assistive technology design for aging populations, and physiological computing applied to games, simulations, and social robots, taking an interdisciplinary approach to his research agenda. John is originally from Colombia and obtained his PhD from the Universidade da Madeira in Portugal in 2018, conducting research under the CMU/Portugal Partnership, and most recently worked as a postdoctoral fellow and adjunct professor in the Systems Design and Engineering Department at the University of Waterloo. John has previous industry experience as a UX research scientist and consultant, including collaborations with researchers from NASA Langley. Dr. Alan Pope is a pioneering psychologist at NASA, studies how cockpit design affects crew performance. He is well known for his research on pilot vigilance, hazardous awareness states, and biocybernetic adaptation, technology adapting to humans. Dr. Pope retired from civil service in 2016 and is currently a distinguished research associate at Langley, conducting research with brain-computer interface technologies for future human factors, applications in cognitive training, system adaptation, and human autonomy teaming. Chad Stevens is an aerospace technology researcher with NASA Langley Research Center in the Crew Systems and Aviation Operations branch since 2009. Mr. Stevens earned his BS in psychology and an MS in psychophysiology. He has performed extensive research in the field of human factors with over 10 years of experience in the conduct of human subject research, experiment design, and aeronautics. At this point, I'm going to turn it over to you, Dr. John Muñoz.
Thank you all. Thank you very much for waiting, and apologies again, we have some technical issues to start before starting this webinar. So I hope you can all see my screen right now with the slides of the presentation. Would you like to confirm? So today I'm going to briefly try to introduce you to the latest inventions that I've been working together with Dr. Pope and Chad Stevens related to the field of biocybernetic adaptation. For the ones that are not very familiar with this topic, we will try to bring a brief introduction to the field. It's also widely known in the academia as physiologically adaptive systems. And basically, I'm going to try to bring some of the motivations that we have behind some of these inventions. We have two particular inventions that I would like to introduce, and both Chad and Alan will come and help us to disentangle and provide more specific feedback on the why we ended up creating these inventions and the whole process of what we envision for these inventions, the different scenarios to be used. The second invention, the first invention relates to biocybernetic adaptation in the specific application of training for de-escalation. The second one talks more about a pervasive and more ubiquitous or omnipresent and decentralized system that can be used in daily life activities. The presentation has been structured in a way that we will introduce the technology, and we will try to bring specific applications, also called embodiments, in the inventions, patent inventions, to show you some of the examples where this technology can be used and how specifically it can be used. For the ones that are not very familiar with this topic, in a sense, what we have is a system that gets data from different body sensors and specifically uses that data. Think of your smartwatches, think of chest strap sensors, think of headphones that nowadays can record physiological data from multiple sources and use that as an input. That data is then recorded and transmitted in real time and is is analyzed and interpreted by a system. The system can be either a computer, can be a mobile phone, can be a virtual reality headset. And then at the end, the system provides a particular output that is the result of an analysis in real time of those physiological signals. And then the signal is transformed into an action in the interface that the user is feedback to the user as a way of visual, auditory feedback, haptics, or any other kinds of feedback that the user can perceive. So the potential or the key benefits of using this kind of physiologically adaptive systems is in some of the scenarios that we're going to show today, you will see that it has the potential to improve the performance because there is a level of awareness from the user of the physiological regulation of the physiological performance, which we don't normally have access to. Think of when you were running and eventually you will have access to your heart rate data by using smartwatches, and how that awareness of that heart rate in real time will be able to help you to modulate the intensity of the exercise that you have. So that's kind of like the principle of this type of technology. So by monitoring continuously this particular information from the body, we will be able to create a sense of awareness of those body signals, and also will be able to track the physical well-being using different sensing modalities. More importantly, we specifically will be able to create systems that can dynamically adjust to different kinds of feedback. And this will certainly provide a skill acquisition by allowing users to access information that would not be able to access otherwise. More importantly, when we create adaptive systems, the intention of this particular adaptation is to create more personalized and tailored experiences. Experiences that can tailor to your level of stress or your level of fatigue, or think of when you're playing games, see if the game will be able to adapt to your level of frustration or arousal, offering a better and ideally more engaging and more efficient experience when, for instance, you were training. This field, the field of biocybernetics, or also called adaptive biofeedback, has certain differences once compared to traditional biofeedback. Traditional biofeedback, you may have the feedback, or you may have a direct feedback from the physiological signals. And this feedback in the classic or conventional biofeedback comes in the way of let's say, you looking at the signals in real time. So what you will see is a lot of the physiological responses on the screen, as opposed to an interpretation of the signals as is done in the adaptive biofeedback. You may have some limited interaction with raw signals when you're seeing on a screen in a conventional biofeedback, versus the possibility of including this as an adaptive or as a more interactive interface in games or simulations in the adaptive biofeedback scenario. Something that is also conventional in biofeedback is the require of an active control. So you as a user will have to create certain level of regulation skills or methods such as breathing or having a concentration of neural signals in order to modify them in real time. But when using adaptive biofeedback, we could also allow the machine to adapt synchronously to the kinds of desired signals that we want, using a more passive control of as a methodology for the adaptation. So moving on, I will try to briefly explain some of the aspects of this first invention called Biocybernetic De-escalation training system. I'm getting one of the quotes from the patent that says, to provide psychophysiological self-regulation training is specifically geared toward helping individuals de-escalate conflicts in real-life scenarios. So the intention of this particular invention comes to scenarios where there's an interaction between multiple users, and that there is a need of one of the users to have a particular approach towards de-escalating the situation and becoming more aware of certain body signals that will reflect a more heightened or a more fight and flight state of mind. So one of the embodiments that we have been exploring in the last 5 to 8 years has been working with law enforcement officers, specifically police officers. And the purpose of this particular embodiment looks into building more resilience and building a sense of awareness, body awareness in the police officers when they are interacting with civils. The key components of this particular invention relates to having a body sensor, having a monitoring sensor for stress response. And we have been using heart rate monitors such as armbands or chest strap sensors to collect data from police officers in real time and being able to transform this into a stress meter or a stress metric that can be used in real time. The system will then use the recording cardiovascular information, process it in real time, and provide feedback to the officers with, for instance, simulations and virtual reality, and adjusting particular elements of the simulation. The data is collected normally using wearable sensors, which will offer a less obtrusive way of recording body signals, and the stress levels could be computed in real time using a computer system that deals with the simulation. The feedback, as you will see, relates to different changes in the virtual environment that can be achieved via interfacing the Biocybernetic system with the simulation. As a way of showing how are we creating this and shaping this technology, we have been working with a company in Hampton, Virginia, called JNF Alliance, which have been helping us to build these technologies together with police officers. So we've been working with police departments in looking at the best way of recording this information, specifically body signals in real time from the police officers, and creating models of how does stress look like seen through the senses, or sorry, the lenses of body signals or body sensors. So we are particularly interested in looking at stress and arousal levels, and we have been recording multiple police officers when they're going through different kinds of simulations using different virtual reality technologies, from full body VR to more or less complex setups. The one that you're seeing on the screen is one that works with full body motion capture and creates or allow us to work directly with simulations that are crafted working together with trainers from different police departments in the US. So from this particular system, what we are using is a synchronization of the physiological data with the simulation data to create psychophysiological models that would allow us to better understand stress, fatigue, and other important human factors related to simulations of police officers when they are encountering daily life situations with, for instance, people with mental health issues. From here, and considering this particular system, we are able to modify things in real time based on the particular model that we have created from police officers, reinforcing the importance of building the self-regulation skills and resilience in them. So a lot of this has been made thanks to the work that was done in the past in NASA Langley with Dr. Alan Poe and Chad being the co-authors of a lot of those patents. A second interesting scenario on this is an embodiment where an airline and customer service will require certain training to deal with customer service. We're looking in frontline staff who will be able to benefit from training self-regulation skills and allowing to identify triggers and things that can produce certain levels of physiological arousal that will prevent people to de-escalate a conflict or de-escalate a situation that may become hostile or violent. The key components of this embodiment, again, are related to the use of wearable body sensors to record signals unobtrusively. Think of smartwatches that the staff and frontline participants will be able to use, and a computer to process that information, or a mobile phone that will allow to create this processing pipeline. Think of we will be able to monitor perspiration levels and provide real-time information to the frontline staff when they are probably getting very irritated, or they are getting extremely frustrated by interacting with users. The system, for instance, could provide real time by vibrating, using haptic feedback, or again, using any kind of simulation for training. And then this information will be feedback to the users and allow them to better identify certain triggers or strategies that are working to relax and try to de-escalate the situation. A third interesting embodiment that we thought of this invention would involve educational settings, and we'll try to look into training teachers in managing disruptive student behavior while trying to maintain the calm during a classroom interaction. So in this particular embodiment, we look into simulated classroom scenarios with unruly students, where some of the behavior of those students will be intentionally designed to create a certain level of frustration on the teachers. We will try to, the patent provides specific ideas to adjust the virtual students' behavior to reward teachers' self-regulation skills, such as, again, respiration or any kind of a de-escalation strategy that they are using as a way of rewarding the behavior and the use of the strategy when the virtual students, for instance, are becoming more and more on roll, or more and more difficult to de-escalate. Again, the invention certainly provides very specific details in the way that metrics will be able to refer to specific psychophysiological states recorded during this particular context, and how to adjust the content based on those inferred states in real time. So some of the benefits that we foresee of this particular invention relates to the improvement of certain social skills. Think of law enforcement or specifically police officers dealing with agitated citizens, or soldiers interacting with civilians that instead of escalating the situation due to very unconscious responses or natural responses that one may have, providing certain self-regulated responses due to previous training with this kind of systems. More in the gaming or in the simulation side, you will be able also to create games that adapt and respond to players' physiological changes in real time. So the games will be able to be certainly more tailored to the particular responses that players may be having, creating an optimal state of flow, which is a state in psychology that is well known in game user experience, to certainly maximize the engagement during a gameplay time. And again, part of what we are trying to do with the systems, specifically working with police officers, is looking more deep into the decision making in high stress situations. And in our particular case, virtual reality has been one of the most interesting technologies that allow us to simulate that in a very safe and controlled manner, which normally is preferred by trainers. So before moving on to the second invention, I'm not really sure if there are some questions, or I would like to encourage participants in the audience to write down any kind of question that you may have for us. And towards the end, both Alan and Chad would join me to try to provide more insights into how the inventions will be able to be used in different scenarios. So the first invention, if you probably have noticed, relates more to specific moments or the use of this self-regulation training systems using biofeedback, in particular for certain situation, scenario, or context where there's not necessarily a continuous recording of the body signals or a continuous interpretation of the body signals. In this second invention, we targeted scenarios where we are constantly using, let's say, the same wearable device. Think of a ring, a headset, a helmet, a chest strap sensor, a nerve band, and a smartwatch. Any kind of wearable that is constantly recording physiological signals, and you use your phone to synchronize those body signals, and then devices and IoT, specifically digitally connected devices around your settings or your daily life activities will be able to connect to that continuous recording and an analysis of those signals continuously recorded to make adjustments in real time for again, to looking at improving the experience that you're having. So this particular invention looks into things like when users are navigating the daily life venues with real-time insights and into their physiological signals, and trying to provide feedback and motivation by using that kind of information. So the first particular scenario that we were looking for this embodiment is an adaptive virtual ambience for aircraft deck. And here we were looking into the life of pilots under training that require certain systems and work with simulations for training different skills before going to the field. This initial embodiment was the result of some of the initial research conducted in NASA Langley, looking into how pilots specifically were feeling and the different psychophysiological states that were measured during their conventional training using, again, simulators. So over here, what the researchers at NASA Langley started doing, we're looking into particular cognitive functioning using things like electroencephalography and looking into state of awareness of the pilots and collecting this information to try to adapt the system to allow the pilots to gain skills in self-regulation that they would not be able to gain using all the kinds of training. So this is a video from the 90s where you will be able to see Dr. Pope and Chad working together and exploring the simulations and working with pilots and pilots under training, looking into certain mental states of awareness and exploring specifically EEG markers that will relate to those states. The main idea with this was looking into specific human factors that will affect the performance of pilots and how to create systems, in this particular case, biofeedback systems that will allow the simulator to adapt in real time and to create modifications in the simulation, in the virtual environment, to create a more, or to facilitate the creation of those self regulation skills. This is a more modern simulator that we use here in the University of Waterloo, where we have also been trying to create or use more wearable systems and devices and modify elements in the environment of the simulator that will change based on the interpreted signals in real time. So, for instance, the environment will change, or certain failures of the system will be activated or deactivated depending on the mental state recorded in real time. One of the most interesting embodiments that we documented for this particular invention was the use of biofeedback modulated video game systems. This has been in the core of the research for the NASA modulation team, where the main goal was using modern video game systems to create adaptations to improve the way that people enjoy games, to look into engagement, ways of measuring engagement in real time using physiology, and to create real-time adaptations of the game difficulty based on those states. So the functionality of this system normally requires, again, any particular wearable sensor that will be able to record signals to infer states of engagement or flow, and allow the gaming system to define certain game variables that will change based on those measured states. In this particular case, brain data, for instance, EEG data can be recorded using sensors that are attached, for instance, to the player's headphones, or directly to the controllers if we are working with sweating activity, and the data will be streamed and used by the video game console or system to modify the game parameters in real time. And again, similar to what we have done in the past with the system, we have worked together to define specific ways of using this information in games. So these are 3 examples of how we have used this, and some of the prototypes that have been created both in NASA Langley and outside NASA Langley to explore the use of the physiological information to adapt or to create real-time modifications of the game difficulty using the inferred states. For instance, here you can use the physiological information as a control input, changing the challenge, for instance, when it comes to aiming on a shooting game. The aim specifically will change the stability when you are getting to a better flow or a more engaged and focused and concentrated state, allowing you to perform better by shooting more clearly and let's say in a less chaotic manner. So this requires using directly the physiological information to adapt the input, in this case, the stability of the aiming. But you can also modify that in a more passive way to adapt the difficulty of the game, for instance, allowing more or less enemies to show up, or allowing your ammo, your different weaponry to have particular behaviors depending on how well you are self-regulating yourself in terms of physiological adaptation, in terms of physiological signals. So for instance, you see here that it would be more difficult for you to kill an enemy if you are in a less engaged or a state of more destructive or less focus, as opposed to when you are completely in more of a flow and engaging mental state. So this is a more passive way of using it. The second example uses a very similar and more modern technology, in this particular case, virtual reality technologies with headbands to basically modify the way that the virtual reality content is presented to the users. So over here you see the environment changes, and the environment gets populated or starts raining or changing the different game parameters, has a way of rewarding participants getting into that flow state. When you're also confronting certain enemies, if you keep your calm and are more relaxed, you will be able to defeat, for instance, this giant spider after completing 30-40 seconds in a certain particular calm state. But these are specific ways that we have been documenting and we have been prototyping when using biofeedback and specifically adaptive biofeedback strategies to modify games and virtual reality simulations in real time. The last embodiment that we have for this one, I mean, we have put at least something between 7 to 10 different embodiments for each of the patent and inventions that I have presented today. And these are just 3 of the 7 to 10 that we have put on each of the inventions. So the third one that we would like to highlight, this one is when new cars and new car systems are becoming more and more digitally connected to your apps and to your different preferred digital devices, such as smartphones or smartwatches. So imagine how specifically cars will be able to use your physiological information collected from your wearable devices to help you to become more alert, specifically when we're looking at driver readiness to, for instance, switching between autonomous vehicles or autonomous behaviors. So what we envision here is by allowing your system to connect to your car, the ambient device, which will be installed specifically on your car and will help you to monitor your signals, will help you to compute those readiness levels and then activate or deactivate certain functionalities of your car, for instance, related to the autonomy of the car or some functionalities of the car that will allow you to create those self-regulation skills when you are probably not so much of alert when you're driving. So again, we created this particular invention not thinking of a very specific use case in a defined setting, but more into different settings and how to create a system that will create this type of feedback in a more dynamic way and in a more ubiquitous way, as opposed to something that only happens once in a specific setting. Some of the benefits of this particular invention relates to allowing for more mobile and ubiquitous biofeedback. That means something that is teaching you in a more continuous fashion how to create those regulations and how to improve your self-regulation skills using the unobtrusive recordings with wearable devices, again, such as rings, headphones, or smartwatches. This type of regulation is more uninterrupted, so it happens more continuously, and there is some interesting research being done in terms of how effective this continuous biofeedback can be, as opposed to the biofeedback that only happens, for instance, in clinical environments. Last but not least, this type of adaptation is certainly more context aware. So depending on the context that you are, you will get a type of behavior of the system that will certainly reward or encourage you to continue improving the self-regulation skills and the training, and certainly will allow you to become more aware of your body signals, even if you are not specifically on, again, certain setting or very specific setting for biofeedback training. So there's the process for licensing some of these technologies is fairly simple, and there is a full and entire catalog for exploring the how easy this could be. Probably he or Nicole could eventually come on and provide more feedback in the way that this technology can be licensed. But you can just, as simple as looking at the inventions and the catalog, set the terms, sign up the agreement, and then you will be able to utilize these inventions for your particular products and systems. These are the two inventions that we are here describing today, and those can be found in the online catalog of the NASA Technology Transfer Program. So after this, I think we are open to questions. I also would like to invite Dr. Pope and Chad to help me maybe with some of these questions and providing some of the insights into how these inventions work, and some of the envision scenarios that we had for these ones. Thank you all for your attention.
Thank you, Dr. Muñoz. All right, we have received a couple questions in the chat. So first, we are going to take Paris's question, which was, how did you deal with user data privacy? Was that a problem that ever came up?
This is Alan. I'll just say that it didn't actually come up explicitly, but when we conduct research with these technologies, we get an informed consent process to take place and have the project reviewed by an institutional review board. And in the case of the police project, we had the police chiefs and the department sign off on this. You want to add something to that, John?
Yeah, I will say specifically when working with law enforcement and police departments, we normally need to do an agreement and explore, especially with the trainers and the police department, what's the best way of handling this data. So normally it is handled locally within the police departments, and each user certainly has access to their own data. So there's something that is always there, the raw data, the easy, for instance, the heart rate or heart availability data that we collect. They will be able to access it in a similar way that they access, for instance, the Fitbit data of the smartwatches that they use. So one of the things that sometimes we need to clarify, especially with the ethics boards, is something that is called incidental findings, and that comes down to things that we are not specifically looking at, but because our sensors they have some level of sensitivity, we'll be able to capture certain behaviors, for instance, of the heart rate or the heart rate variability that may be considered atypical. So what we do normally is establish a certain protocol for informing participants about it, but always recommending them to go and talk to their medical doctors first, because most of the sensors that we use are wearable sensors that are not medically grade, but but are research grade instead.
All right, thank you so much. We're going to go to the next question now. So the next one we have is from Kalman Horvath, and they are asking, could you potentially be able to detect and estimate psychological status of people in distress with the use of non-invasive measurements, and then relay that information to the specialist to help them de-escalate?
Well, that is something that could be done. And this makes an important point that once you start thinking about this, other ways to apply it, other ways to implement this technology come to mind. And I would encourage you to look through the patent applications themselves and see the different embodiments that we've proposed. This is not one of them, but see those that we've proposed and see what they stimulate in your mind about what could be done with this kind of technology. Because this is an exercise in imagination.
All right, thank you, Dr. Pope. From Jake Easton, we have another question. Has any work been done with rehabilitation centers or prison rehabilitation confinement centers to analyze system effectiveness pertaining to the first invention regarding biocognitive analysis?
So in the field of physical rehabilitation and neurorehabilitation, I've seen multiple examples of physiological adaptive systems being used to improve the outcomes of the therapy. So if you think of systems that are able to, for instance, measure the levels of physical fatigue, or measure the levels of cognitive function, specifically certain cognitive skills, and we'll be able to feed that back to a therapy that is, for instance, computerized, or a system that uses games or simulations for it, you will immediately recognize the potential of feeding back this information to the system. I'm currently working with a group of developers and designers in New Zealand, looking into the application of adaptive biofeedback for inmates in New Zealand. And the goal that they are looking at is how this digitally connected apps and games working with biofeedback would be able to reduce violent behavior in inmates. So there's not a lot of research being done in that particular field, in the field of mental health, specifically for prison rehabilitation and confinement. But it seems, or the hypothesis here is, by reducing or by improving the emotional regulation of the inmates, the overall center will benefit from potential reductions of the overall violence. So answers will be more of a yes and no, because unfortunately there's not a lot of information in that case. Chad, I don't know if you want to add to some of those points.
I'll point out, this is Alan again. You asked what type of feedback would you provide to the officer? I want to point out that this is, when we're talking about the de-escalation training application of this, we're talking about a virtual reality simulation that the officer is training in. That differs from the ubiquitous other invention, in which where you're providing feedback through the Internet of Things and that kind of mechanism in the real world. But in this application, as you'll read in the application, it proposes changing the behavior of the person that the officer is dealing with in the virtual reality scenario, which you couldn't do that in the real world, of course. But you can do that in a virtual reality by changing the character's behavior to be more cooperative. If the a police officer was exhibiting calm and collected physiological signals, just to reward them through the behavior of the individual that they're interacting with.
Chad, I think you were muted before.
Okay, if Chad doesn't have anything to add, I'm going to go to the next question, which Dr. Pope kind of already touched on. It's from Ralph DeVerna, and he asked, in a high-stress police scenario, what type of feedback would you provide to the officer? Would that feedback be relayed to a central command? Additionally, how do you plan to handle data processing locally?
Yeah, I think in a complement as a way of complementing what Dr. Poe just mentioned, we are initially working with VR simulations. So that means a lot of VR elements or the simulation elements are the ones that will eventually change. But VR aside, what we could potentially do, for instance, and I've seen some researchers working on this, is pairing the physiological information with something like the body cam, and looking into potential ways of exploring activities of daily life for police officers and how that relates to certain changes in their physiology, specifically with simple things such as heart rate, but you can think of more complex metrics such as arousal or psychological stress, and looking what are the specific things that the police may encounter in their daily life activities that will create certain peaks of stress that probably could be not really optimal for their daily lives. So I've seen some of that research being done here in Toronto, and I think that's definitely something that complements what we're trying to do in VR. Is we assume that by training these skills in virtual reality, there's going to be a transference of skills, or that kind of ecological validity is something that is still part of the research into how extend these skills that you train in VR with or without biofeedback can be transferred to the real life.
I'll just add to that.
Yeah, I think we can hear you, Chad, but not too loud.
Is that better?
Yeah, better now.
Okay. Sorry, WebEx is not cooperating with me either. So on the last point, I think this is another example of a use case that we didn't consider. Not that we tried to be, completely inclusive of all use cases in the patent applications, and that's what part of the tech transfer process is commercializing these technologies into many different areas. So our thinking is in training for the most part, and how to incorporate these capabilities in a training context. So the officers would be, as John presented, they'd be given this biofeedback, biocybernetic enabled feedback in training, so they could develop those skills, and then those skills would transfer to real-time or real-world operations. But the question is great because it points out how to extend into a different use case, and then the last part of that question about how to handle the data, and is if it's going to be relayed to the central command, and how it's processed in real time. Those are considerations that would be very interesting to discuss with potential licensees and develop a commercial product that addresses those questions.
Thank you so much. We're just going to do a couple more questions. I wanted to double check. We had a question in the chat about the TRL. So is it a 0.75 and a 3 for the TRL of the two technologies?
I'll try to take a stab at that. So I think the de-escalation is a higher TRL, and that's due in large part to the work that John has been leading, especially the VR test cases that he presented. The pervasive biocybernetic adaptation, that one's a lower TRL because we don't have anything beyond concepts as far as a prototype for that technology, but they do rely on similar physiological sensors. So those parts of each of these inventions are highly similar. So I think, yeah, the lower TRL would be for the pervasive biocybernetic adaptation, and then the higher TRL number is for the de-escalation capability.
Okay, perfect. We have another question from Jake. He's asking, have there been any attempts to associate this technology, Invention II biofeedback, with a Neuralink system?
I think a lot of the technologies that we always try to use are really non-invasive, wearable systems, commercially available. So our understanding with the Neuralink system is certainly very different to those features in terms of, like, it's normally very invasive because it requires opening the scalp and inserting and implanting a sensor. So I think, yeah, we're going certainly far away from that, and we always try to use wearable systems that are commercially available, and we look into the best way of interfacing those wearable sensors and communicating multiple wearable sensors, and centralizing that information and accessing the raw data, and defining our own metrics, which is part of the experimentation that we have been doing with multiple sensors in the last decade. And there's been some interesting developments in terms of standards for communication and allowing sensors to stream the data, and some elements of privacy as well. But yeah, we normally don't work with invasive systems.
Thank you, Dr. Muñoz. All right, I think we're going to do about 2 more questions. So we have one from AB. Have you or are you using these for astronauts training and or operations? If yes, what kinds of scenarios have you explored?
I'll speak to that, and then definitely allow Alan and John to add to what I say. So currently we don't have any active capabilities for astronaut training. We do have and develop some proposals in that area, specifically for long duration space flight, enabling technologies that involve biocybernetic adaptation. So the scenarios would be for that we proposed have been on the ground training prior to the mission start, and then continuous training while on the long duration journey, and then continuing to practice with the system, the biocybernetic system, while on station. So those are some proposals. Some of the technologies, not these two technologies, but some of the other NASA technologies have been adopted at JSC and used in some projects there with a focus towards astronaut training. But they have, to my knowledge, they haven't been fully deployed And then I have to give credit to our colleagues at NASA Ames who did actually deploy biofeedback training technologies with astronauts quite a few decades ago now. Autogenic training was developed by Dr. Pat Cowings at Ames, and Mae Jemison actually tested that technology on space flights, and they demonstrated the efficacy of that to enable operations in the microgravity environment. So I'll stop there and ask John or Alan to add anything they might be aware of.
Okay, do you have anything to add, Dr. Muñoz?
Probably has mentioned by Chad, we also have been working with some researchers at the Canadian Space Agency and some of the manufacturers of different sensors, also here in Canada, looking into ways of integrating this more, looking into long-term and long specifically for missions where the mental health of the astronauts or of the crew will be potentially affected by the long duration of the mission. So we have, again, some very detailed concepts and scenarios also created specifically involving nature-like sceneries and sensors that are embedded already within the virtual reality headsets that will facilitate the integration of this technology into this kind of missions. But again, we're still looking into the best way of developing further these concepts.
Thank you. We're going to do one more question from Mino Park. Considering the suite of physiological signals you collect to provide insight into cognitive states/operations, are there other metrics that you are interested in exploring? Things like body/effector positions via motion capture, EMIS, etc.
So I can briefly talk to this. We normally, certainly when using and working with this feedback, although we can consider this type of kinematic information, physiological signals, we tend to sometimes differentiate between movement-related physiological signals, like the ones that this person is mentioning, like working with inertial measurement units or motion capture sensors, from the ones that we record more from electrophysiological signals or even optical sensors that allow us to record some of those body signals. So I've seen and we have been working on a kinematically adaptive system for stroke rehab, again using sensors such as inertial measurement units to facilitate and infer elements related to coordination or related to range of motion in rehab. So this is something that also has been explored before. And I think nowadays with the sensors and the amount of information that we have available is easier than it was in the past to certainly develop games and adaptive systems that will react to kinematic information from what it was in the past, where we just didn't have access to those sensors and that information.
Okay, I think that is about all we have time for today. If we were not able to get to your question during the Q&A, we will follow up with you by email within the next week or so. If you have any additional questions, please feel free to email them to the email address on the screen, and we'll be sure to follow up with those answers as well. Once again, I just want to say thank you to all of our inventors here that presented, and thank you to all of the participants who came and took the time to be with us today.